Okay, so moving points, part 2. This class is so special that only Qatar is here. And so last time we talked about like lines, right? Like we have things like lines and points, right? Like if 2 points with degree A and B, so 2 points A and B, right? We have like degree A, degree B, right? The statement that these coincide is degree A plus degree B at most, right? If we have 3 lines concurring, right, then that statement that they concur is equal to, or has degree as like the sum of the degrees of the 3 lines, right? Things like that. And I introduced the fact that we can animate a point on a conic, right? Like t squared minus 1, 2t, t squared plus 1 will parameterize a point on a circle, the unit circle. But besides that, I didn't really like say anything about what you can do with conics. And now is the time. So the first lemma should be in the handout. So on a conic, which we are going to say on a circle or on the unit circle, for example, just because, so if we have the equation x, I'll draw this with my mouse, x squared plus y squared equals z squared, right? Then we can transform this to any other conic by replacing x with some combination of like x, y, and z. We can replace y with some combination of x, y, z, and so on for z. And all the statements that I make about the unit circle will still hold for any conic because we can transform x squared plus y squared plus z squared to any conic through like this method. Right. Okay. So if we have 2 moving points, A and B, on the unit circle, then the degree of the line AB, line AB, is at most degree A plus degree B over 2. So normally this would be degree A plus degree B. In this case, it's degree A plus degree B over 2. And when A is equivalent to B, we in fact have that the line AB goes to the tangent line from A or B to the conic. So when I talked about like Zach's lemma, right, line AB has degree A plus degree B minus K, has this degree at most, where K is the amount of intersections of A and B. I said that if like T equals T0, right, this makes A equivalent to B. Then if we use this case T equals T0 to reduce the degree of line AB, then we can't then we don't know what line AB looks like at T equals T0. So we can't use it when we're defining, or when we're counting special cases at the end, right? So, okay, you're still muted. Like the equation for degree A, for line A plus B, is like something x plus like something y plus something c equals 0. And then basically t equals t0, making these coincide, means that t minus t0 is a factor of all of these three things. But when we divide t minus t0 from this equation, right, we have no handle on t equals t0. So basically, when we reduce the degree, usually when we reduce the degree of a line through Zach's lemma, then we like lose the ability to use a certain point as a special case. So it's like a trade-off. But in this case, there is no such trade-off. We know what line AB looks like when A is equivalent to B. So to prove that line AB has a degree at most, degree A plus degree B all over 2, we can first prove the following statement. So we're gonna have A be represented as some like point like this. And we have that P of T squared plus Q of T squared equals R of T squared. So what we can show is that there's polynomials ST such that P of T is S squared minus T squared over 2. Q is ST, and then R is S squared plus T squared over 2. So this looks familiar to like if you do like NT with like Pythagorean triples, like primitive Pythagorean triples. We assume that P, Q, and R are irreducible, meaning they don't share a common factor. So this is like exactly the same, and it has exactly the same proof as well. Yeah, I'll just write this. There exists ST such that, okay. So we can just say like Q of T, equals P of T, actually, R of T squared minus P of T squared. And this factors as R of T minus P of T times R of T plus P of T. I like how both of the geo classes going on right now are like, they're like technically geo, but like we're both just doing algebra at this point.
Yeah.
So we can say like this is, so these two factors are they don't share any factors because like if they did, then R and P would share factors. Right. So we can just say like log P R, right, share. I believe we can do this. Right. So we can say, so, right, like we can just say like one of these is S squared, one of these is T squared, and we're basically done. right? We get like P is like S squared minus T squared over 2. R is like S squared plus T squared over 2. Q, I don't know why I'm writing equivalent, equals ST. So now we can use this to like show what we want, right? So the line, I'm not gonna write like S of T. I'm just gonna write like, well, okay, so we can just homogenize. We can just multiply everything by 2. So this is the equation of A, and then B can be similarly represented as x squared minus y squared, 2xy x squared plus y squared. And then the line between them, so x plus y plus z. We are going to be here for a while. Strap in, have fun. 2xy s squared plus 2xy t squared minus 2 st x squared minus 2 sty squared. That's a minus sign. And then y is s squared x squared plus s squared y squared. Actually, the s squared x squareds will cancel out, just speed up the process. Should be 2t squared y squared minus 2s squared x.
You can just say left to reader as an exercise.
Yeah. No, I totally know that. It's just I was going to leave the next thing as an exercise to the reader. Yeah. Because the next thing is even worse, arguably. Right? Like I can get through this thing like decently fast, maybe. Yeah. This should be right. Okay, if it's not, then like you didn't, it's your fault for not catching me. Right, equals 0. So this is the equation of the line. And what we can first do, we can simplify this. We can get rid of all the 2's. I'll just like strike it out in some other color. There's no red. That's unfortunate. Well, we got orange. But the more important thing is that we should be able to factor all of these. Let's see if I know what I'm doing. Believe we can factor tx minus sy from all of these. So the first one will be like tx minus sy times like, do I want to actually do this? Or will I just like kind of cheat? I think I might cheat today. Yes, I will cheat today. Times Sx minus Ty. And then the second one is Tx minus Sy times Tx plus Sy. And the third one is Tx minus Sy times minus Sx minus Ty. So in fact, we can cancel this factor from all three coordinates, and we can look at the maximum degree of the resulting polynomials, which is basically like max degree of S or T times like max degree of X or Y. So if we go back here, the max degree of S or T is the degree of A over 2. And same thing for X and Y. So the max degree of S and T plus the max degree of X or Y is the degree of, is less than or equal to degree of A plus degree of B over 2.
Wait, why is max degree degree a by 2?
Why is it
Like,
dA by 2? Okay. Well, okay, so if degree S and degree T are not equal, right, then we get that the, like, let's say degree S is bigger, then these two are both 2 times degree S, and that can't be more than the degree of point A, which is like the max degree of the 3 coordinates. Do you see that part?
sorry, I disconnected for last 30 seconds.
Yeah. So,
Can you?
okay. So, so if ST degrees are not equal, then we have the degree of these two things I underlined are 2 times degree of S, right? We can say S is bigger degree, and that has to be less than the degree of A.
Oh,
Right?
yeah, of
Yeah,
course.
because A, yeah, if they're equal, like at least one of these is like 2 times degree, has degree like 2 times degree of S, right?
Yeah, it works.
Mhm. So this gives us two things, right? Okay, so first of all, thank you, Kritarth, for letting me know I can do this. It is left as an exercise to the reader to show that using these three, if A is equivalent to B, then the line AB goes to the tangent from A to the conic. Right, you get that like all three of these are like well defined when A and B are equivalent. Right, this is like S squared minus T squared 2ST minus S squared minus T squared. I even helped you a little bit. Right, so this is one strength of what I have here. So the other strength is that this also proves that if we have PQR as the coordinates of A, P squared plus Q squared equals R squared, and they're irreducible, then by looking at this representation again, we see that the degree of A is even. Right, if S and T don't have the same degree, right, S is bigger, then the degree of A is 2 times degree of S. And if S and T are equal, then it's just 2 times the degree of S as well. S and T are equal degrees. So this proves 2 results. So we have like degree A plus degree B over 2 result is shown. And then we also have shown that degree of A is even. Right. So I think before I move on to the next thing, I will showcase a problem that uses both of these results. Well, this isn't really like a problem that you would find on Olympiad, but like whatever. Okay. Have a circle. We have a line tangent. And then our setup will be, we have a point A that has degree 2. And then the circle from A, the other tangent circle to this line that passes through A. Okay, so passes through A, tangent, so in tangent to our line here and our circle here. And we want to find the degree of the center. So before I start, do you have a way to bound the degree at all, Kurtars? Or to
Wait,
like
I didn't get
describe
the
this?
question. So like you're having an arbitrary point A
Yeah,
and
with
like
degree
you,
2.
yeah, with degree 2, and then you're drawing 2 circles such that they're tangent and passing through it. You want
Okay,
to,
this first circle is fixed. This first circle is
oh, okay.
fixed.
Oh, right.
And
So,
then point A
okay, right.
moves on the circle.
Oh, fine. Yeah, so we want to find the locus of the center of the other circle.
Well, more than the
Cusp,
locus
I
of the
think.
center, we want to find we want to bound the degree, but like good.
Yeah, makes sense. Okay, so like,
So can we define this more in terms of lines, perhaps?
so maybe we can draw the antipode,
Of what?
like of A with respect to the fixed circle.
Okay. And what do you see from this, perhaps?
That this has degree 2 as well, right?
Yeah.
And
So you're saying the line like this line?
yeah,
Well, while you are right, we can also use the fact that O has degree 0 if we say this is the center O. So line OA has degree at most 2.
oh, right, of course, yeah.
Okay. Okay, so what we can do is well, okay, so the center of the circle is on line OA, right? And then it's the intersection of line OA with the perpendicular from this tangency point to the line. So how can we define the tangency point? If like
Like
A,
maybe we can use the angle fact, like points at infinity and equal angles. So like the degree of the line perpendicular would be 1, I think. With that,
so you're
uh,
saying the degree of this line is 1?
I mean, okay, it depends on the degree of the what do you say?
This tangency point?
Yeah, it depends on the degree of tangency point.
Yeah, so degree of this line is the same as the degree of this tangency point by the Zach's law.
Wait, how?
Because the line between this point and the point at infinity, and that point at infinity
Oh,
perpendicular
fixed.
to this line is fixed. It has degree 0.
Right.
Right. So how can we figure out like a bound on the degree of this tangency point?
Wait, so uh aren't we already done though? Like we know that O has degree at
Well, what is the degree of the tangency point?
um it should be at most 3,
And
like 2
why?
plus 1. Like
So where is this +1 coming from?
uh wait, where is it coming from?
Yeah.
Mm, wait, what was I thinking?
Okay.
Right. Like degree of the center is 1. No, it is not. What? I'm confused. Wait, so
Okay.
what did we
So
get it from before? Like the point at infinity thing?
okay. So to find the a bound on the degree of this center point, right? We can define the center point as the intersection of line OA and the perpendicular from this tangency point to the line. So this reduces the problem to like finding the degree of this tangency point,
Yeah.
right? Because by Zach's lemma, this line has the same degree as the tangency point
Yeah.
because yeah, it passes through a fixed point, which is the point at infinity perpendicular to our original line.
Hmm.
So to calculate the tangency point, we can actually define the tangency point as, so we take this like topmost point on our circle, we draw through A and it intersects that line at a point, which must be the tangency point by like homothency,
Yeah.
right? So this actually gives us a full description of the degree of O prime. So if we say this is like T for top, right? I'll say this is P because I can't say it's T for tangency, right? Then line TA has degree 1.
Wait, isn't it degree 2 because A is moving with degree 2? Oh, right, yeah, degree A by 2. Yeah, fine. Right.
Divide by 2.
Yeah,
Yeah,
yeah.
it's very
Okay.
nice.
That is useful.
Right. Another thing we technically could do is just Zach's lemma. Because like line T and A intersect like once.
Oh, right.
And so the intersection of this degree 1 line and our degree 0 line, so P, right, has degree at most 1.
Yeah.
And then O prime has degree at most 3,
Right.
right? Because line OA has degree at most 2.
Mhm.
But this is not actually the end of the story, because what we can say is that O prime actually lies on a parabola.
Oh.
Actually, this is a bad depiction of the parabola. It looks some more like this. And we can define this parabola. So if we say like, so this distance here is OA, the distance between those two, right? Then the distance OO prime and the distance from O to L prime is the same.
Yeah.
So O prime actually lies on a parabola.
Which
And
is
what
another
this
degree 2.
well, we can have degree 4 points on a conic, but what this tells us is that the degree of O prime is even, right?
Oh, yeah, right.
So the degree of O prime can actually be reduced even further to just 2.
Yeah.
Yeah. So we can use, so like these two lemmas, and in particular this one, are both pretty powerful.
Yeah, makes sense.
Well, in the sense that especially when we use this one, it's kind of like hacks, right? Like, so we found that degree of O prime is at most 3, but it has to be even. So
Yeah.
like the end, right?
Said.
Degree of O prime is 2. Well,
Right.
technically at most 2, but it can't be 0. So it is 2.
Yeah. So we
Yeah.
are doing NT and Geo at this point.
Yeah, I think, well, especially with like an argument like this, we're just doing like NT or algebra at this point.
Yeah.
Right. It's great. Okay. So the next theorem allows you to deal with conics in a much less magical way. So, but it is pretty powerful in itself. But this is the reason why moving points is bad. Like this one lemma, basically. Besides that, you have to be careful. So this is like, well, I'm giving like the most general versions of the lemmas that are used in moving points. Typically, you'll usually see like a much more degenerated version of all of these when you actually use moving points. But I think it is nice to have the general version. And the general version states that if we have a moving point with degree A, or a moving point A on a circle, or a conic, we're just going to say the unit circle And we have another moving point just anywhere with degree b. Then this intersection point, degree less than or equal to degree a plus 2 times degree b. And the scary part about this is this 2 here, because it makes conics and moving points bad. Because let's say like we calculate the degree of this line to be like 3, right? 3 is a manageable number, but then we want to deal with this point, right? Okay, so let's say we calculate the degree of b to be like 3 and degree of a to be like 2 or something. Right, 3 and 2 are mostly manageable numbers, but then we want to find at this point. This point has degree less than or equal to 8, right? And 8 is a big number, right? 8 is very scary.
Yeah.
Yeah, I agree. So when you're doing moving points, it won't always work, right? You can get a lot of multiplication pretty fast, right? And you don't want to be dealing with like a degree 16 problem, right? So if you're unable to use moving points effectively, right, then you're just unable to, right? You should not like force moving points on a problem necessarily, because if there's a lot of these intersection points with circles, it'll go badly really fast.
Then
Yeah. So what we do is we can show, okay, so let's say the coordinates are xa, y, a, z, a, and xb, yb, zb. And let's just say the conic is x squared plus y squared equals z squared. Then then what we can do is say that the second intersection point, here we go. Is show that this point lies on the line AB and the circle x squared plus y squared equals 0, or equals z squared, not 0. So showing that this point lies on the line is not too bad. So first, let me explain the notation I used here. It's kind of janky. So basically, you multiply this to each of these. You multiply this to each of these. And then you like add that, right? So the x coordinate of the point will be xb squared plus yb squared minus zb squared times xa minus 2 times xa xb plus ya yb minus za zb times xb. And the y coordinate and z coordinate of the new point I've constructed will be defined similarly. And so to show that these are all collinear, Well, we can think of XA, YA, ZA, right, times some constant plus D times like XB, YB, ZB, right? And then from what I said earlier, well, a possible way to do this is to just like bash the determinant, right? Well, it's not really a bash. Right, like CZA plus DZB, right? XA, YA, ZA, XB, Y, B, ZB. The determinant of this is 0, right? Like you can just subtract C times XA, YA, ZA and D times XB, YB, ZB from this top row. And then you get 0, 0, 0 in the top row. So the determinant is 0. So we just need to show that this lies on the conic x squared plus y squared equals z squared. And that is left as an exercise.
Definitely will try out this exercise.
Yeah, I think you'll have a lot of fun with it. I tried this like a week ago, and I definitely had a lot of fun. It's actually not as bad as like it initially looks, because you get like a lot of things canceled, but like it's not very enlightening, I think. Here, I'll just write this. So that if people are looking back at these slides, they have some semblance of what's going on. And then it is also another exercise for you that you will definitely try, right? To show that this point indeed has degree at most degree A plus 2 times degree B. Actually, it shouldn't be that hard, right? Like this thing is degree A plus 2 times degree B. These are 2 times degree A, or degree A plus 2 times degree B at most, and you add them.
Yeah, works.
Great. Okay. So what this is usually used for is A is fixed, right? So if we say A is fixed, right? And then we have like a degree 1 line going through A, then B has degree 2. Notice that this is like the converse of what I said earlier, right?
Yeah.
So if A has 0, B has degree 2, then line AB will have degree 1. And it's also worth mentioning, if we draw the tangent line, the second intersection will just be A itself. I think before I get onto that, I want to highlight one more thing that I'm not sure I covered last time. So if we have a degree 1, this should be in the handout as well. If we have a degree 1 point, right, that can be represented like this, then I think before I had a like, so for any line ax plus by plus cz equals 0, I had a parametrization, right? And basically what we can do is we can transform pt, qt, and rt, right? We can make linear combinations of them, to get the parametrization for some x with by plus z equals 0. So we get that pt, qt, rt lie on like a times dx plus e1 plus fz plus b times like gx plus hy plus iz plus like dot 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 equals 0, right? So basically, oh, hi Gunjan. I think you have like no idea what's going on at this point. Okay, have fun. So P, Q, R have degree 1 at most. Then we get that this moving point lies on a line. I believe this is in the handout somewhere. I'll just share that handout so Gunjan can see. I'm having problems like downloading and posting, so I'm just sharing the overleaf instead.
Should I try to download instead?
If you can, that would be great.
Whatever.
And we can do a similar thing for conics. So for the unit circle, we had the parametrization t squared minus 1, 2t, t squared plus 1. And then if we have pt, qt, rt are all degree 2 or less, then we can say like pt equals like t squared minus 1 times some constant d plus 2t times constant f plus like t squared plus 1 times some constant g. And what we can say is that pt, qt, rt, this point lies on the conic like plus like some linear combination of x, y, and z squared equals some linear combination of x, y, and z squared, which itself is the equation of a conic. So here, I'll write this for people reading the whiteboard later, right? Deg 2 points lie on a conic. So now we can get to, I think, like a like decently involved problem. I mean, the other ones were also involved, but like this is involveder. So this should be on the handout. I wonder if I can like cut and paste. I'll try to do it.
I sent on the Discord, by the way, the PDF.
Oh, okay, nice. Okay, wonderful. You see this?
Yeah.
So the point to animate has already been like given to us per se, right?
Yeah.
So what? Here. So okay, whatever. So we have I. Imagine ABC is labeled in the correct way. E, F, G. This is A, right? So my drawing is kind of bad, but like I, right, is not necessarily on like G, E, F,
Yeah.
M, and then we reflect this point over line BC, and we can see point D down there. And we want to show that G, I, M, D cyclic. So in general, this is kind of scary with moving point, this kind of problem, just because of like the circles. But we will see it's not actually that scary. So the first thing we can do, so we let, so I'll start this one off. Center of like AEF. Okay. So actually first, let's say we animate I, right? We animate I and we say I has degree 1, right? Because it's lying on the angle bisector. So I has like degree 1. So E and F have degrees what?
1.
Yes. Line BI has degree 1, right? Zach's lemma. Its intersection with AC has degree 1 by Zach's lemma as well. E and F have degree 1. But what about O prime? O prime. So how can we define O prime in a more moving point stable way? Right, like in the last class, we had a similar sort of setup.
Intersection of perpendicular bisectors might get to a high of a degree, I guess.
Well, if we look at the perpendicular bisectors of AE and AF, these don't get that high of a degree. So the perpendicular bisector of AE, right, is like nice because this midpoint also has degree 1, right? I think this is written somewhere on the handout. I covered it last class. Degree. So this midpoint has degree at most degree of A plus degree of E, which in this case
Yeah.
is just 1.
But
And
the
then we want
perpendicular
the,
bisector is also 1, right?
yeah, because this passes through the fixed point, which is perpendicular, which is like point at infinity,
Right.
perpendicular to AC. So line between degree 1 and degree 0 thing is degree 1 by Zach's lemma. Similarly, this one is degree 1. So O prime, in fact, has degree at most 2.
Right.
Okay. So how can we define G well? Using what we already have.
It's a Mickel point, but
Yes,
is that useful?
I don't in fact think so. Well, it can be used actually. There's a way. I think if I would do that. Actually, that would be pretty nice. So I'll continue with this and then I'll explain like a way to use Mikhail point.
Right. Okay.
So
hmm.
yeah. So in fact, that actually might be a good idea. But like what we can do is we can let this be O and we let this be a line O prime.
Right, and then reflect.
Yeah, and then well, we can draw the perpendicular line from A to this line and intersect it on the circle.
Hmm. So, okay, O has degree 0,
Yes.
O dash has degree 2,
Yes.
O dash has degree 2 as well.
Here's the thing though. We can actually say it has degree 1 because when I is like, so in the case I is on line BC, we actually have that O is equivalent to O prime, right? Like E will equal C, F will equal B. O will
Yeah.
equal O prime.
No, no, oh, never mind. Oh, right, right. Yeah, fine.
So Zach's lemma works.
Yeah,
And then
right.
another way to think about this as well is O prime moves on a conic, right? Because it has degree 2. O is on that same conic. So line O prime has degree at most 0 plus 2 over 2.
Ah, that's nice.
Yes,
So, okay, so we
right.
have O dash is degree 1.
O dash, right? Degree 1. And then
Then,
the
yeah,
perpendicular from A to that line.
that is degree 0. So that is degree 1. Wait, what? 1 second.
Yeah,
Yeah, it is degree
so
1.
right, the point at infinity of O dash has degree 1. So the point at infinity perpendicular to that has degree 1 as well.
Yeah,
And line from A to that has degree 1.
right.
AG, take 1.
But then A
And
is
then,
fixed. So,
well, A is fixed, but line AG has degree 1. So basically, we can use this second intersection point lemma. So A has degree 0, right? Point at infinity has degree 1. So G has degree
2.
2. Yes. So G has degree 2, and this is quite nice. For our purpose. So a main step was this, right? So if we didn't do that, then we would have G with degree 4. And
Yeah,
that starts getting to the scary territory because we haven't even dealt with GIMD cyclic.
right.
So there is another way with Mikhail point, which actually might be nicer, right? Alternate dig G calculation. So we do the same strategy, but I think this is how Mikhail point works. Yeah. Yeah. So if we say this is E, this is F, then line EF passes through a fixed point by projective.
Yeah.
Let this be B, and we do the same idea, but on like circle FBL instead.
Oh,
So
right.
I believe this method is actually pretty nice because, okay, so the degree of this, so perpendicular bisector of LB deg1 or deg0, perpendicular bisector of BF is deg1. So if we say this is O1, right?
Yeah.
O1 has degree 1, and O, so G has degree 2. Line O01 has degree 1, line BG has degree 1, G has degree 2.
Yeah.
So I think the advantage of this method is that with this method, we can use the special case F equals B, right? In this method.
Oh,
So in the previous method, when we reduce the degree by saying O equals O dash, right? Reduces degree B. We don't know what the conic that O dash lies on looks like, or at least we're too lazy to find out, right? So when this point I is on line BC, or when line F, or when F equals B, we really can't do anything with that special case. So I don't actually know what this special case looks like, I guess, when we're doing the actual calculation, but we can find out. So to calculate G, I, M, D cyclic, so what we learned last time is that if we have 4 lines, L1, L2, L3, L4, then the intersection of like L1, L2, L2, L3, L3, L4, and L4, L1, right? L1 intersect L2, L2 intersect L3, L3 intersect L4, L4 intersect L1. Degree, so cyclic. So if these 4 points cyclic, then that's degree at most L1. Okay, yeah. L2, L3, L4. So in some unfortunate instances, L1, L2, L3, and L4, neither of them are particularly nice. And we have to find all of their degrees through, so like, let's say we're proving GIMD cyclic, right? We would have to define line L1 as just line GI or something, right? And then line GI isn't particularly nice. So we'd have to say its degree by Zach's lemma is degree G plus degree I. So in the unfortunate instance that we have to do that with like all of the 4 points, then this statement is 2 times the degree of GIMD, right, when you add it all together. But we are not that unfortunate. So let's go back here. So is there a setup that, so what is the setup of the 4 lines between G, I, M, and D that reduces the degree of our final statement as much as possible? So I'll actually just write the degree of all these lines so far. So line GI is deg 3. Line GI, to my knowledge, or at least according to our diagram, is not really that special. GM, actually GD, is deg 2. GM is degree what?
2, right? Because M is
It's
fixed.
actually 1 because we can divide by 2.
Oh, right. I always forget that.
Yeah, okay, I'll rewrite this nicely. 3 GD 2 GM 1, and then ID is 1, IM is 0, and D is 0. So if we go back here, right, like the constraint, right, on L1, L2, L3, L4 is that we're sort of looking at it like cyclically in a sense. And we want to find the 4 lines that go through like G, I, M, G, D, like cyclically, I guess. So we can't have GI, GD, GM, and ID, for example. And we want to find one that like minimizes the sum of their degrees.
So we can get 4 without too much difficulty.
Yeah, so what is that setup?
Like, did I miss like GM?
GM, wait, what did you say?
Wait, let me
GM,
once again. GMMD, DN, DGN. Okay, no, you get GI. No, wait. Yeah, but you can still do like okay, wait. GI. Yeah, GI ID. Wait, no, not GI. I mean GM.
mhm.
Okay. No, that
What's your
doesn't work
idea?
either.
Okay.
Interesting. Yeah, yeah, okay. GM, MI,
Mhm.
ID, and GD.
Yes, this works.
Yeah.
So the kind of counterintuitive part is that we don't have MD in this setup, even though MD are like 2 fixed points, because of the realization that line IM is also fixed,
Hmm.
and line GI, which
Is
you'd have to
that
include if you have MD, is bad, right? Okay, degree for statements. And I want to see if I can actually copy paste this thing out of the way. for whatever reason, keyboard, you can't do backspace for delete. You have to do like X. Okay, whatever. I'll just write it here. GM is 1. MI is 0. ID is 1. GD is 2. Deg for statement, and we need 5 cases. So this is, depending on the problem, the first part might be tricky, trying to reduce the degree, but usually it is this part, because in the, I think the only example of a problem I've given so far, we had to do special cases like Pappas, and Pappas, the special cases are not hard to find. I'll make this a lot smaller. Maybe that's a little too small, but it doesn't matter too much. There. G I M D A B C. So a thing you have to be, so this is either like an advantage or disadvantage, but you have to be careful about making sure that you follow, well, so you're basically dealing with a like sort of different problem than the given one, right? We're not really dealing with circle AEF, we're dealing with line OO prime and the perpendicular, right? So things like this you have to be careful about. Like when E equals A, right? Like what is the perpendicular bisector of AE? So if you just say this question regularly, it doesn't make any sense. However, we've defined the perpendicular bisector of AE as the line between the midpoint of AE and the perpendicular point at infinity to line AC. So the perpendicular bisector of AE is actually well defined. And actually, like, that actually just gives us our first case. E, F, right. So if I say I equals A, we get like O dash equals A, G is A, I is like A, and then to finish off, what we want to show is that the points at infinity of line GM, MI, ID, and GD are all like follow the like rotation pattern I described in the last class, right? So GM will have line this, same point at infinity of this line, and then ID will have same point at infinity. No, wait, hold on. Like we, so GM M have this point at infinity, and GD ID have this point at infinity. So we get that the angle between the point at infinity of GMGD is the same as the angle between the point at infinity of IMID. Hence, we're done, right? Like saying GIM into D cyclic is a little silly and a little ambiguous when G equals I, but in fact, the problem is well defined. when we're looking at our moving points setup. And another thing to note is that when G equals I equals A, it's not a degenerate case because we're never using line GI. So that's the end of that case. So I equals A is one possible case.
We can take the incenter as well, I guess.
Can we? So tell me how. Because when we do incenter, we get like this sort of thing, right?
Oh,
EF,
those are not
yeah,
the in-touch points. That's
yeah,
sad.
unfortunately. I was afraid you're gonna start like rattling off some like big brain Feuerbach or whatever. It's like, please don't. This is not that scary.
If we use the Mickle point, we can like Mickle point solution, we can also use AI cap BC, right?
Yes, so I haven't actually tried this, but I have high hopes. I'll erase this real fast. I'll have a slightly bigger diagram. So the Mickle point version. So what we do is we now, what we have, I guess, is a definition of G, even in our sort of degenerate case. I, B, C, these are E and F as well, because we defined the perpendicular bisector of line of BF to just be the point at infinity perpendicular to AB and the midpoint of BF. Okay, so the perpendicular bisect, this perpendicular bisector exists. Let's say this is L, this perpendicular bisector exists. And then we can intersect the circle again. G. Yeah. Okay, so we want to show G, I, and D cyclic. I'm not sure how this is gonna go yet, but I think we can start by looking at angle LGB, and let's say this is O1 as before. So this is equal to angle O1 BL, which is angle ABL minus 90, I think. Okay, let's see if I can like do math. Yeah. So if we draw this line here, then I think we should get that this is like the top point. Can you
No, right,
verify that?
because AL is the top point. Because it's the external bisector, right?
True. Okay. Let's imagine I didn't say that.
Wait, so are LO1 and A collinear? Oh no, they're not, of course, because 90 degrees.
uh, wait, oh, AB, oh, hold on. Yeah, that's what I was doing. So, if we say like this is C prime, and A, B, C prime equals like, okay, B, yeah. So I think this is like perpendicular here. Because if we say this is C prime, then we have B, C prime A, and like Z form an isosceles trapezoid. Like angle, so the arc like BZ, or no. Okay. Try 2. Let's see if I can do angle J's anymore. Oh, okay, I'm very silly. Of course, okay. So if we say B prime is the antipode of B, then angle BGA is 90 plus angle, or yeah, BGA prime is 90 plus angle ABC prime. And so we want to show like B prime G A prime equals like the arc like A prime B prime is the same as arc AC prime. That means A to this line is parallel to BC. Okay, finally I can angle chase. Okay, does this actually help? I think we can try this maybe for like another 5 minutes. If I can't do this case, then like move on to the other cases. I think we can end this class at like 12:30 maybe. I start a little late.
You mean like 20 minutes, 23 minutes from now?
Yes, yeah,
Yeah,
23
yeah.
minutes from now. Yeah. Oh, I forget. Yeah, IST, IST so sad. Uh, So another thing to note is there's like not like a technique itself, but like it is possible to do nested moving points, I guess. So the idea is that our special case is itself difficult, right? But it's easy to define with moving points.
So like
So
you move another point.
yes, yeah, that's what you do.
Right.
So I mean, in this case, I think what you do is move A. So I feel so degrading to be going to this level. Um, so I think L would have degree 1 in that case. So if we move A, right, the line between A and this midpoint intersects BC at L. L has degree 1, right, because of the divide by 2 lemma. A prime has degree 2. G has degree 4. Yes, 4. Remember, degree of A prime plus 2 times degree of L. I would have degree 1 because we intersect line AM with line BC. Line AM has degree 1 by the divide by 2 lemma. And then D has M and D have degree 0. And wow, this has a lot of degree. Yeah, I think degree would be like in that 7 range. So moving points is not always possible, unfortunately. Okay, because it has been our 5 minutes. Actually, I'll keep this. Second moving points is impossible. So I know that this problem does have some synthetic solution that is like not that bad, but that's not why we're here. So I don't actually know the synthetic solution. So I'll just actually write here like in BC case.
So like in this case, this case ended up being too hard. So like you could not get any
Well,
information from this case.
yes, I guess. This case did not simplify the problem necessarily.
Yeah, makes sense. Like G is still weird, I guess. So that's why.
Yeah, unless my angle chase is wrong and G was nice the whole time. But I think I finally got the angle chase to be right. So there are some other special cases
Midpoint
that we can
department.
deal with. So I think this case is similarly annoying. Maybe it is possible to extract some other information. This is a straight line AC.
Wait, so what do
And
you have to prove is cyclic in that case? You'll get a degenerate thing, right?
in fact, you will not. And the reason is that we never actually we never defined line IM as a line between I and M, right? Like the line IM is fixed.
Yeah.
So what we basically end up showing is that like a g or a like angle AMG equals angle MDG,
Hmm.
which just means that angle bisector is tangent to the circle. Right? I think it looks something like this.
Hmm. So like,
I mean, we can try this case for a small while. I believe this is just about as non-trivial as everything we did. There is like the lemma where move that.
you get some random similar triangles, but we are doing
You,
MMP, not Geo. So,
I don't know. We are doing geo. What are you talking about? Remember, I did an angle chase eventually.
oh yeah, yeah, right.
Yeah. So like you do get like this parallelogram here actually. I'm not sure if this helps in like any other ways.
Sad.
Yes. So that we had some failed attempts.
Okay, let's go for another failed attempt. Point at infinity.
Well, you kind of failed at making another failed attempt. I
Oh
believe
no.
this one is. I believe this one actually does work pretty well.
Llama.
Yeah. So now we have two cases that work. Right? We just need three more. It's important to remember that a degree 4 statement, you need to show 5 special cases.
Alright.
So I believe this one does work.
Mhm.
Okay. I'm just gonna get very tiny. It's very small. Looks something like this. And we say G is like the intersection point. In this case, it's like defined, okay. And we want to show that G, M, D, and I are cyclic. And this sounds kind of silly at first. But okay, so if we look at it in terms of our moving points lens, so the point at infinity of GM is like that point there, let's say, right? The point at infinity of GD is actually the point at infinity of IM is like here. Point at infinity of ID is here. So we want to basically say that the angle between the points at infinity of GM is the same as the angle between points at infinity of GD, which means we want to show that the point at infinity of GD and GM is the same.
So GMD collinear.
Yes. And in this
That isn't
case,
bad, I guess.
do you see what's going on? Why
Is it
G is the arc midpoint?
is it just the reflection or something?
Yes. Okay.
Hmm.
I plus A worked. I equals point at infinity works. Okay.
3 more to go.
Yeah.
Not looking forward to it.
Okay. So instead of thinking about which points I are nice, you might want to start thinking about which points G are nice,
Yeah, makes sense.
right?
So we can define it in we can once we know G, we can define EF and all that nicely as well
Yeah,
using the
sure.
Michael point thinking.
Mm-hmm.
So let's say we take G as the midpoint of arc AB.
Will this actually work? Hint, hint, I have not tried this yet, but like, I trust you to like know what you're doing with Geo, so like,
No, I have no clue what I'm doing.
thanks for
Okay, no,
giving me
it
a lot
does
of
not seem
money.
useful. Silly.
Okay.
Okay, which other point G is nice?
I feel
Maybe
like
G. What?
once I say this, you might be a little annoyed. But okay, continue.
G equal to B?
Yep, that's what I was thinking.
Yeah.
This actually, okay, let's try this. This is M, and we have D here, and I'll actually, okay, here, this is I. And we want I to be such that, so A, B, F, E. Uh, uh, oh, whoops, I am muted. So A, B, F, E are cyclic. Do you see what's going on here? Perhaps.
Mm, 1 second. So wait, what?
Hmm?
mm, so CI cap AB supposed to be wait, that can't be true, right?
What cannot A, B, F, E cyclic?
No, you're defining like E or F whatever that was is CI cap AB, right?
Mm-hmm.
So you'll get AB and E collinear.
Well, F, right?
Whatever that was.
Yes.
Oh right.
So,
Oh right, that works fine.
so the reason this is not bad is that we can just say I is such that BI perpendicular to AC or parallel to AC. And then we can retrace, I guess, our steps with the defining O dash.
Yeah.
So we'll get perpendicular bisector of AE. So E is point at infinity. So midpoint of AE is also point at infinity. It's the same as E. So the line between E and then that other point at infinity, perpendicular line to AC, is just the line at infinity. Right? E is a point at infinity, and then we're making a line with another point at infinity.
Right.
Right? So we intersect this with the perpendicular bisector of AF, which means that this intersection is just the point at infinity perpendicular to AB. Right? So O dash is point at infinity perpendicular to AB. And line O dash, right, perpendicular to AB, AG, right? So G is B when we let BI be perpendicular to, or parallel to AC. So do you see why G, M, I, D are cyclic in this case? Or B, M, I, D are cyclic when we have BI parallel to AC? So what we can actually do is we can literally just angle chase this one. What we get is like BDM equals like BAM, or I'll just make this like MAC. Right? We can say like this is N, BDM equals like BNM equals like BAM equals like MAC equals MIB, right? BIAC parallel. And that's it. BMID are cyclic.
Oh, wait, how did you find BDM?
It's, remember, D is the reflection of N over BC.
Oh,
Yeah, remember
okay.
all those years ago when I defined D?
I thought it was a reflection of N across M.
Oh, oops. It is in fact not.
Okay.
Oh, yeah,
MMP, let's say, ignore geo and focus on
we
calculating
can't
decrease endpoint.
we can't ignore geo, sadly. So so BI parallel to AC works, and we actually get two cases now, right? BI parallel AC, CI parallel AB works up to the left. Oh no. That means he must have come back and then left. Okay. So we have four cases and we need a fifth one. And this fifth one, time is running short. So I'll give you like,
Geo homework.
no, I won't give you homework. I want to actually finish this problem. But I'll give you a short amount of time once I'm done. drawing diagram to figure this one out.
What is I?
That is I.
Thanks.
Well, to guess a good point for I. Looks more like that. Oh my
Which
god.
point is that?
I'm just drawing a random I.
It satisfies that thing. Like,
But
is AEFI cyclic?
not in general.
No,
But
but like in the case you're taking.
yes, it is.
Uh,
AFI. So that is a final case we can take.
mhm.
Actually, there are two cases, in fact.
Oh
So
no.
so this case is actually pretty nice. You're gonna have to do some geo though. It's not bad, right?
Mm.
So this is the reflection of circle ABC over line BC. I lies on this circle. GI. Yeah. Yeah. So AEFGI cyclic. And we
Mhm.
want to show GIMT cyclic.
Mm.
Uh,
Mm.
do you see why if I lies on this circle, then AEFI cyclic?
I lies on BI. What? Which circle?
This one.
Yeah, but
Reflection
like,
of ABC over line BC.
oh, yeah, because 180 minus A.
Yeah, 180 minus.
So the D lies on that circle.
Oh, it does. You're right. Okay. D does lie in the circle.
And G. Okay, let's do some languages. Mm. Mm. Wait, M is not the center of that circle, is it?
It is not.
Yeah. Um,
I feel like my drawing is a little suggestive that like
yeah,
M is
I
the center of the
understand.
circle.
But
But is it?
how do you find the angles though? Okay, so by radical, okay, no, you can't even do that.
Okay.
Mm. Hmm. So like MD is obviously the perpendicular bisector of BC. GI cap. I give up.
Okay. this is actually kind of nice. So if we let, so this turns out to be like, so I'm just saying M dash, that's the midpoint of BC. And the reason is that if we let this be I dash, right, IB, I dash C is parallelogram, we can do some angle tracing. AGI is like AFI is like 180 minus A minus ACI equals some other stuff or something. I'll just do it up here. AG. Uh-oh. There are like these weird sections of my touchscreen where I can't draw. And then if we let this be B prime, B prime parallel to AC is like 180 minus A minus like B prime AI and actually minus B prime BI prime is like 180 yeah, which equals like A BI prime. Right. So GI prime collinear. We get that like G M prime times I M prime is G M prime times like I prime M prime, which by power of a point is N M prime times like M
Wait,
prime
what's B
M.
prime?
Huh? What's
What's
what
B
prime?
prime? B prime.
M B prime? B prime parallel to AC,
Oh, okay, right.
right? Equals dm prime times m prime. So by power of a point, we're done. Yeah, this is slightly scam, not scam, but just like, but it is kind of nice though.
Yeah. One sec, let
And
me just. Okay, what? I'll take the screenshot and save it.
so I on like your BHC, you can figure out what H is, right?
Yeah.
So we actually have one more case than necessary, then we're done.
Yeah.
Yeah, yeah. So that's a problem with moving points, and the difficult part about this problem was more just choosing the special cases, because there are like two special cases we saw that like don't really help,
Yeah, but they
and
look
the ones that,
nice on
yeah,
first sight.
and the ones that are nice are kind of wacky.
Yeah.
And one more thing, so in this problem it was fairly obvious what to move. In some problems the points that you have to move might not even be in the problem statement, or it might not be obvious, or like the problem might be itself a special case of maybe something more general that can be more easily solved with moving points,
Damn.
right? Like if I give like this problem again, right, this case, if I create a problem saying like prove this case, right, like this is
Yeah.
hard, but if we let I be some other points, it's easy. So sometimes that is true. I don't know how to actually spot those, but sometimes it is easier to spot if it like looks like it has a generalization. But yeah. That's all of MMP class number 2.
All right, then I guess I'll stop recording.